Hi everyone, welcome to the live section of this course, which is Quantum Transport. So I'm Gitanjali. I'm a PhD scholar from IT Delhi, and I'm the TA for this course. So in the last week, we have gone through some of the concept related to quantum transport in ballistic region. We have also seen transport in the diffusive region. For today's class, we will mostly see the effect of the single electron effect in the presence of in a metallic quantum dot or in a semiconductor quantum dot, and under what condition we can achieve a single electron tunneling. So we'll cover in brief the concept related to this. So let's start from the basics. So transport, if you recall, it's nothing but a transport of it's a kind of charging and discharging process, if you recall the lecture. So we add one electron from one side of the conductor, and we just collect the electron from the other side. So this is the way transport can happen inside a device. But if you consider a normal conductor, then the charge in this normal conductor, they flow continuously without any. So if you see the graph, I is directly proportional to V. So this is the Ohm's law that we have seen for normal conductor. But when we decrease the size of conductor to a order like in nanometer scale or in a micrometer scale. In that case, we can also take an example of quantum dot. It can be a classical dot. So in that case, where the scale is it's much less than the normal conductor that we talk about. So in that case, what will happen? So electrons inside the conductor, they will experience a strong Coulomb repulsion, and this strong Coulomb repulsion, they will prevent the flow of charge carrier through this small nanoscale device. So in contrast to what we've seen in the normal conductor, where we see the charge flow continuously, when we decrease the size to a nanometer or to a micrometer scale, in that case, we will see that there will be a reason where the flow of electron won't be allowed, and this is because of the single electron charging effect that we'll see in detail. So for that case where the device dimension is in the order of nanometer scale, so in that case, the current they will show a oscillation, which we call a Coulomb oscillation, Coulomb blockade oscillation. We'll see in detail, and also the charge that is present, that can tunnel through this nanometer device, nanoscale device. So they vary in a step-like manner because of this Coulomb blockade effect or the single charge effect. So let us see what are these cases. So for discrete electron charging, so if you want to see the effect of Coulomb blockade, which is also related to the discrete single electron charging. So to see this effect, to see that the electrons tunnel one by one through this barrier and current is suppressed or it is blocked across unless the gate voltage aligns the energy levels properly. To see this effect, we need two conditions to be satisfied. So the first condition is that the thermal energy, which is the KBT, it should be much less than the charging energy, which is electrostatic charging energy, and it is given by E square by 2C sigma. So C sigma is it's the total capacitance of the circuit by taking the gate capacitance into account or the source and drain capacitance into account. So this is the net capacitance of this circuit. And to see this Coulomb effect, we need that the thermal energy, it should be much, much less than the charging energy, which we call as AC. And what it will tell, it will ensure that there won't be any fluctuation in the charge because of this thermal energy, because thermal energy will this will smear out the current, the oscillation in the current. So we won't see the discrete nature of this charging effect if the thermal energy is greater than the charging energy. So to take an example, so if you consider a normal conductor, so for normal conductor, we can take AC, which is given by E square by 2C sigma. So E square, it will be in the order of minus 10 to minus 19 square. So we are just checking the order, not the absolute magnitude. And sigma, C sigma, it is of the order of some nanofarad because these are large conductors, so capacitance is very large. So this will be in the order of 10 to the power minus 9. So this, if you see this is mostly 0 because it is in the numerator we have 10 to the minus 38 and then in the denominator we have 10 to the minus 9. So the charging energy for the normal conductor, it is much, much negligible. So that is why when we charge, when we apply a voltage to a normal conductor, we won't see any charging, single charging effect. We see that the current flows continuously and the typical IV characteristics, it follows the Ohm's law for the normal conductor because the capacitance for that case is very large. But now when we decrease the size, for example, if you take a gated quantum dot. So for that case, the C sigma, because the size is very small and the capacitance, it depends on the geometrical size of this device. So when the device dimension is already less, so C sigma is, the capacitance is very, very less. It is in the order of 10 to the minus 18. Correct. So for that case, the EC, we can't neglect the effect of EC. So is EC, the charging energy will be significant. So because the charging energy is significant, we see that for this case, we see that for a given range of gate voltage or the source drain voltage, we see that the current is 0 because the charging energy is very high. So the charges which are already present in the system, they repel the charge that we are trying to add to the system. So that is why, because of this strong electrocoulombic repulsion, the current will be 0 for some reason. And whenever the gate voltage exceed this energy scale of charging energy, we'll see that there will be a peak in the conductance because of the tunneling of the charge carrier to this quantum dot region, or we say the quantum or the conducting island region where the quantum dot is present. So this is one of the condition to see the Coulomb blockade effect. But this is not sufficient, or this is not a sufficient condition. So even though we have a higher amount of charging energy, even though the thermal energy is less, then even in that case also we'll see that the charging Coulomb blockade effect is we won't see any Coulomb blockade effect unless and until we satisfy the second condition. So the second condition to see the Coulomb blockade effect is that the tunnel resistance. The tunnel means the resistance that is present between the source and the quantum dot. There should be a tunneling region, and also in between the drain and the dot there is a tunneling region, and the resistance of this tunneling region, it should be very large. So how large is the tunnel resistance? For that, this tunnel resistance should be much greater than the quantum resistance, which is h by e square, and this is in the order of 25.8 kilo ohm. So the tunnel resistance of each barrier. So we have a case like the dot is present and it is connected to it is tunnel coupled to the drain and source. Also, it is capacitively coupled to the gate voltage. So this tunnel resistance RT, which is connect between drain in the dot and the source in the dot, it should be greater than the quantum resistance, which is h by e square. And this condition, if you recall the lecture, it was derived by taking the Heisenberg uncertainty principle for the uncertainty in time and energy. So if you take delta E delta T greater than equal to h cot by 2, and if you put the delta T, which is the characteristics time for charging and discharging, so this would be given by the RC time constant, RT into C. And from that, you can get a uncertainty in energy. And this uncertainty in energy, it should be much less than the AC, the charging energy. So that even though there is a spread due to this uncertainty in energy uh, because of this low resistance, then even in that case, if this condition is satisfied, then we will see a Coulomb blockade effect. And from this condition, we get that the tunnel resistance RT should be much greater than the quantum resistance. So if we consider a case when RT is very small, so RT is too small. So for that case, what will happen? Because the tunnel resistance is very less, so the electrons can tunnel easily from source to the dot and dot to the drain. So that means the quantum fluctuation in number of electron in this quantum dot region, it will be very large because it is a continuous flow, right? Because the resistance is very less, so it will allow the electrons to pass through this dot, the tunnel region, as well as the through this quantum dot region very easily. So because of this, we'll see that there will be a large fluctuation in the number of charge carrier present in the dot region. So the number of electron in this quantum dot region, it is not well defined. So because of this, we'll see that this will behave like a classical conductor with continuous charge. So this means without any high tunnel resistance, which is much greater than this quantum resistance, even though the charging energy is much greater than kBT, if the second condition is not satisfied, so if let's say it is less than h by e square, so in that case, the discreteness of this charge, it is it will get smear out, so it will spread out. We won't see any discreteness of charge carrier, and for this also we'll see that there will be uh, it will behave like a classical conductor with continuous charge. So that is why in experiment what we do this for this quantum dot experiment. So we attach this dot with opaque tunnel barrier, which are weakly coupled to the source and the drain, and which is high tunnel resistance. So this is about the two condition that is required to see the Coulomb blockade effect. Now we'll see what is the transition rate of this Coulomb blockade effect. If you have a Coulomb blockade, then what is the probability of electron traveling from source to drain through this quantum dot reason? So for that case, transport of charge carriers across a single barrier. So we'll make two assumptions. One is that these are weakly coupled to the either side. The dot says weakly coupled to either the source or the drain. So that means the wave function psi1 for the source and psi2 for the drain. This will remain unaffected because of this weak coupling. So for this assumption, we can use the Fermi-Golden rule to calculate the transmission probability. Also, we can also write the Hamiltonian as H1, Hamiltonian on the source side, on the drain side, plus the perturbative term, which is related to the tunneling event. So if you use the Fermi-Golden rule, we can calculate what is the transition probability from state I to state A. So electron is traveling from source to drain through this tunnel junction. So this is given by 2 pi h cut psi A perturbative term psi f square delta EI minus A. So this is the transmission coefficient. And delta, it is this indicates that the transition probability or the transmission probability, it is non-zero only when EI is equal to EF. So only when the initial state matches with the final state, in that case only we'll see a transmission non-zero transmission probability. So now if you consider that the number of states, the density of states, these on the source and the drain side. If they are if they are continuous, so they are separated by energy which is much smaller. So for that case, we can replace this discrete formula through integration. So we can write gamma from source to drain. Gamma 1, 2 is 2 pi by h cut minus infinity to infinity T1 to E square and multiplied by the number of occupied states on the source side, and this is given by the product of the density of states and the Fermi-Dirac distribution multiplied by number of available states on the drain side. This is given by density of states on drain side multiplied by number of vacant state, which is 1 minus f of E2 d. So to solve this integration, we can consider that we are mostly focusing in the linear transport regime. So by linear means we the energy difference between the source and drain, it is much less than the Fermi energy. So for that case, for this small energy scale, we can assume that this transmission coefficient, it is independent of energy. So we can write it at T12 and we can take it out of the integral. And also we can take the density of states as independent of energy and take out of this integral. So if you do this, we will get gamma 1, 2 is delta U by E square by H, rho 1, rho 2, T12 square, 1 minus exponential delta U by KBT minus 1. So delta U, it is E1 minus E2, energy difference between source and drain. And this is nothing but the conductance of the tunnel barrier, GT. So now we have gamma 1, 2, it is delta U by E square, GT 1 by exponential delta U by KBT minus 1. So we can consider a case where the temperature is absolute 0 Kelvin. So for T equal to 0 K, we will find that gamma 1, 2 is minus delta U by E square GT for delta U less than 0, because for delta U less than 0, this term will be negligible. So we'll get a minus 1 here. So that is why gamma 1, 2 will be minus delta U by E square GT. And when delta U is greater than 0, so this term will becomes infinity. So this term will goes to 0. So that is why gamma 1, 2 will be 0 when delta U is greater than 0. So this is for the case T equal to 0 Kelvin. Now let us see under what condition this this nanoscale device can behave like a ohmic device, and under what condition we'll see a Coulomb blockade effect. So if we now apply a voltage to this quantum dot, that is a voltage biased junction. So for this case, if you consider that the GT, the tunnel conductance is very less. So we can write the change in energy between the source and drain is the applied voltage minus E times P, and gamma 1, 2, this will be given by delta U by E square GT, and the current is given by mod E times gamma 1, 2. So if we put it here, we'll get that delta U GT by E square, and delta U is E times V. So E square will cancel. We have V GT, or this is B by RT. So this is nothing but the Ohm's law. So under low conductance regime, we can assume that the voltage bias tunnel junction, it will behave like a ohmic device. So it will follow the Ohm's law, V is IR. So now let us see what is the Coulomb blockade effect, or the single electron charging. So for this case, if we add one electron to this quantum, let's say quantum island or the conducting island, then in that case we can write the change in energy of the system as UF minus U1. UF, you can write it as Q minus mod E square by 2C, and initially we have Q square by 2C. And if we solve it, we'll get E by C mod E by 2 minus Q. So for tunneling to happen, we have seen before that the delta U should be negative. So tunneling will happen. This delta U should be negative, or Q should be greater than mod E by 2, or in terms of voltage, we can write V should be greater than E by 2C. So we'll see from this condition, we see that there will be below this limit E by 2C, the current, the tunneling will be 0. So we will get a graph. If we plot a graph between P versus I, we'll see that current is 0 to a point where it is not E by V is E by 2C, and also similarly in the negative direction. So we'll see that for this reason, the current is completely 0. And this is because of this Coulomb blockade effect or the single electron charging effect. We'll see in details in our next part. So now let us see some of the devices which uses this Coulomb blockade effect or the um, single charging effect. So the first one is the single electron box. So this typically behaves like a storage device where we can store a discrete amount of charge. So if you draw the schematic, so it is somewhat like this. This is the conducting island, or could be a quantum dot, or could be a classical dot. And this conducting island, it is, if you see the figure, it is capacitively coupled to this gate voltage through this capacitor Cg, and also it is also tunnel coupled to the source electrode. So there is no drain side here, so we won't see any flow of current for this case. But because there is a, it is tunnel coupled to the source voltage, also it is capacitively coupled to the gate voltage, we'll see that there will be Coulomb blockade effect, where we'll see that the we can increase the charge carrier in this conducting island one by one because of this Coulomb blockade effect. So, single electron box or single electron island, it typically means that it is conductive. There is a conducting island which is connected to the gate voltage by a capacitor Cg, and it is tunnel coupled to a source electron. For this nanoscale device. If you now look at what is the energy of this quantum dot or conducting island. So energy of this quantum, or precisely it is the classical dot. So E dot, we can write it as what is the induced charge due to this gate voltage and what is the charge that is there in this conducting island. So this is square by 2c. So the numerator, it is nothing but the effective charge by taking into account the induced charge because of this gate voltage, also the charge that is already there in the conducting island. So CGVG, it is the induced charge, and Ne is the charge, quantized charge that is there in the conducting island. So we can see that this energy, it is following a parabolic equation. And when we apply the voltage, when we increase the voltage, then what will happen? This parabola, it will shift along the direction of, so this is the parabola. And now when we increase the gate voltage, so this parabola will shift along the voltage axis, and this will detect whether the electron will tunnel into or out of this island. So let us see in detail what is the effect of the gate voltage on this single electron box. So for that, let me draw the plot first, then I will explain what I'm trying to say. So we have a parabola because of this electrostatic energy. Y-axis is the n dot and x-axis is the Vg, Cg. So initially let's say we have zero voltage. For that case, the energy, the parabola, it is centered at this zero voltage on the y-axis and at a point where we have any, and the minima is around the n dot, which is equal to any. So now when we change when we increase the energy, what will happen? So this energy will now increase. So it will follow this parabolic relation. But we won't see any tunneling because the energy is not sufficient to uh, cross this charging energy. So for that case, now we'll meet a point where these two curves coincide with each other. So let us see what is happening in that region. So when we increase the gate voltage, then induced charge will increase, or which is what we say. The CGVZ will increase, but the effective charge will remain as it is. Effective charge will remain as N. So, and when we, let's say we encounter a point where CG, PG is equal to A times N plus half. So this is the point where this two curve or the two successive parabola collide with, they intersect with each other. So they have the same energy um, uh, at the connecting or the touching point. So for this point, so we are considering only n and n plus 1. We are considering the first touching point. So for that case, if you calculate En, so En will be n plus half E minus Ne square by 2c sigma. So this will give E square by 8c sigma. Similarly, if we calculate En plus 1, then CCVG is n plus half E and this is n plus 1 E square by 2c sigma. So this will also give E square by 8c sigma. So that means at the point where CG PG is equal to E times n plus half, or for the next part, next point, we'll see it is n plus 3 by 2 and so on. So for this point, what will happen? This En and the En plus 1 state, they have the same energy. So the energy uncertainty will now increase because the particle can be found in the n state, also in the n plus 1 state. So because of this, the tunneling to this tunneling to this conducting island will now increase. So for this point where these graphs touch with each other, it's possible to see the tunneling. So the charge carrier can tunnel to the conducting region. And after we cross this touching point, we'll see that the particle will stay in the En plus 1 state because this has the lowest energy. So this will stay in the N plus 1 state unless and until it has the next highest energy level, En plus 2. Again, for this case, at the touching point, they have the same energy. The electron will now tunnel to this because the uh, gate voltage is such that it is properly aligned with the source and the it is properly aligned. Sorry, it is properly aligned. So because of that, we'll see there is a tunneling will occur for the n plus 3 by 2. And after that, now the electron will now stay in the n plus 2 state unless and until it does the next parabola at the touching point n plus 5 by 2. So this process will repeat one by one. So what we see that, we'll see that the charge is added to this conducting island one by one because of this Coulomb blockade effect. Okay. So this is the this is all about the single electron box or single electron island, where we can change the charge in the system by a discrete. Next, what we have is the single electron transistor. So unlike the single electron box where it is only tunnel coupled to the source, for this case it is tunnel coupled to both source and drain. So it is possible to see a current in the system now because we have a source and drain. And the drain will collect the current and will see a response to the current as a function of the voltage. So the schematic is somewhat like this. So we have a conducting island which is tunnel coupled to the source. Also, it is coupled to the drain. And it is capacitively coupled to the gate voltage through this capacitor and the gate voltage PG. This is the conducting island or the classical dot region. So for this case, what we'll see that for VDS, which is there should be VDS here. So for VDS less than E by C sigma, so there won't be any current because of this Coulomb-Blockade effect. So graphically, we can say we plot the current versus voltage. So there will be a increase in the current only after a threshold voltage, which is E by C sigma on either side. So this is the response to the source and drain voltage. So we will get a graph like this. So for now, let us see what is the effect of the gate voltage. So we have seen the effect of the source drain voltage on the current. So, and we see that unless and until VDS is greater than E, it is less than E sigma, we won't see any current. And after that, we'll see a current. So now we'll see the effect of this gate voltage. And if you can easily guess what will be the effect, because we have already seen the effect of this charge carrier, effect of gate voltage in the single electron box case. So the effect of gate voltage for this single electron transistor, it is similar to what you have seen in the single electron box. Only the main difference is that for this case, because there is a source and drain, we'll see a current response. And also we'll see tunneling of charge carrier one by one whenever the parabola touches at the charge degeneracy point. So what I mean is that, so similar to the single electron box case, we can write the electrostatic energy for this case is the induced charge because of this gate and the charge which is there in the conducting island divided by 2c sigma. So this is the equation of parabola. And when we vary this gate voltage, we'll see that this parabola will shift in the voltage direction because we are increasing the gate voltage. So we have a parabola because of this electrostatic energy. And whenever two adjacent parabola touch, they touch with each other, we'll see that there will be a turning of charge to the next high level. Like this. So if you have started with n, here we have n plus 1, here we have n plus 2. And this is because at this degeneracy point, En is equal to En plus 1. So we apply a gate voltage such that, so let me start with the schematic. So if you want to understand this, so previously we have En level, which is, I think it's better if I take it here. So previously we have the energy level of En plus 1 is much greater than the En. So because of this energy level is greater, we won't be able to add one electron to this quantum dot region or classical dot region. But now we through this gate voltage, what we have done, we lowered the energy of this uh, quantum dot region. So now the En which was higher earlier, it matches with the energy of this En level. So it lies here. So because of this proper energy alignment, now it's possible to tunnel to add one electron to the system because energy is lowered by means of gate voltage. So because of this, whenever we have a charge degeneracy point, we'll see a tunneling of a charge carrier, and we'll see that the charge carrier in this quantum dot region will increase by 1. And also we'll see that the current will also now increase around this region where we see this charge degeneracy point. Okay. So this is what we call as a Coulomb blockade oscillation. So we see a oscillation in current because of this Coulomb blockade effect. So for this reason, the energy of the levels, it is much higher than what is required to add the electron. So that is why we won't see any current. So the charge will remain constant. But when the energy hit this charge degeneracy point, the point here, then the energy of the adjacent level n plus 1 and n plus 2, they are equal. So it's possible to see it's possible to see the charge carrier in n plus 1 state or in n plus 2 state because they have the same energy. So because of that, the charge carrier will tunnel to this conducting island and we'll see a peak in the conductance or in the current. Okay. And this is achieved as n plus for charge, n plus half. This is n plus 3 by 2 and n plus 5 by. Okay. So this is what we have seen in the single electron transistor. Okay. So now let us see how we can change what is the effect of gate and the source and drain voltage on the IV characteristics. So we have seen that, if you recall, for drain and source voltage, which is less than E by C sigma, the current is 0. The current is blocked because of this Coulomb blockade effect. Now, the question is whether it is possible to reduce this length. And the answer is that yes, it is possible. We can, it's not like we have a, no, we can't tune this. So we can't decrease the size of this region so that we can see the tunneling even under the low value of VDs. So for that case, what we need to increase the gate voltage. So what will gate voltage will do? Gate voltage will lower the energy of this quantum island. And because of that, we'll see that there will be shifting in this curve. Similarly, we can have reason like this. So this is under different gate voltage. So the net effect is that if you plot both the variation of gate voltage as well as uh, the uh, the drain and source voltage, we'll see a point where we'll see a diamond region where the total current, the current is totally 0. So this is what we have seen. If we recall the lecture, we have plotted the 2D plot of I versus VST and VG. Okay, so just to give a brief overview, I think, yes, this is the part where, so if you see this graph, this colored region, these are the point, these are the current region, and in the y-axis we have gate voltage, and in the x-axis we have the drain to source voltage. And the lines, these lines, these are the parabola corresponding to different energy level. Okay. And we see that there is a diamond region that is forming at the around the center of this 2D plot. And this is the reason where we see no transport of current. So inside this diamond region, there won't be any transport of charge carrier. And also if we see the behavior, let's say we are moving along. So we are keeping the gate voltage constant, and we are seeing how the what is the effect of the drain to source voltage on the current. And this is what we'll get. So if we keep the gate voltage constant, we'll see that the current will be zero up to a point, then it will increase exponentially. This is the effect of drain to source voltage. And in the other hand, if we fix this drain to source voltage like this vertical line, and we see what is the effect of increasing the gate voltage, then this is what we have seen earlier. So the current will see a oscillation in the current because of this tunneling of charge carrier to the conducting island. And if you take this part, if we take this diamond shaded region, this vertical line, it represents the periodicity of this Coulombic oscillation. It shows what is the periodicity. And the horizontal line, it is related to the charging effect. Okay. I hope this is clear. So in the next part, we have seen what is the difference between a metallic quantum dot and a semiconductor quantum dot. In metallic quantum dot, we have a continuous density of states in the quantum dot. So that is why we'll see a regularly spaced Coulomb diamond in this plot. But if we consider a semiconductor quantum dot, so for that case, the density of state is not that large. So because of that, we'll see that there won't be any we won't see any periodic variation of this Coulomb diamond. We see that this diamond evolve gradually and it vanishes completely after a certain gate voltage. Okay, so this is all about the single electron transistor and the Coulomb effect. In the next part, I think towards the end of this week, we mostly discuss what is the difference between a classical dots and a quantum dot. So to give a brief, classical dots, like the examples of classical dots, these are metallic quantum dots as well as some larger quantum dots that uh, we can make by using some lithography technique. So the main difference is that for classical dots and quantum dots. For classical dots, the density of states is continuous, but for the quantum dots like a smaller semiconductor quantum dot, the density of state, it is not continuous, and the energy spacing between the energy level, it is significant. Okay, so for classical dot, we assume that whatever energy required to add the electron, it is completely the charging energy, because we see that we assume that the energy levels are continuous. So to add one electron to this system, we only need the charging energy for this case. But in the quantum dots, because there is a significant spacing between this energy level, we see that in addition to this charging energy, we require some more amount of energy that should be added, or that is required, so that it can excite to this next higher level. Let's say we have electron here and we want to add one electron, uh, let's say n plus 1 electron. Okay, so for that case we need this. So this is the n plus 1 state, and we will be able to add this charge carrier only when we add AC with delta E. So only charging energy is not sufficient. In addition to that, we need the energy spacing so that the charge carrier can successively occupy the energy levels. And the difference that we will get is that for the Coulomb oscillation, for the classical dot, we'll see a periodic oscillation. Periodic oscillation, and they are equally spaced. But for quantum dot, the main difference is that because of this delta E, so if we are adding energy to the same energy level, then this they are closely spaced. But in the next case, this level is already filled. Now we are adding energy to this next higher energy level. So for that, the spacing will now increase. So now we'll see that this spacing will increase and it is proportional to EC plus delta E. So instead of equally spaced Coulomb oscillation, we'll see that there is a oscillation, but the periodicity is not equal. So it is sometimes they are small, they are closely spaced. Now they are largely spaced, and this pattern repeat for this quantum dot. Okay, so this is the main difference between a quantum dots and a classical dot. And also we have seen the energy levels of quantum dot. So if you recall the atomic configuration, for any atom like silicon or sodium or any atom you may take, so they say electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6. This I think you are already familiar with. So similar to that case, because the quantum dots have discrete energy level, we can also represent the energy level by closed cell configuration. And for quantum dot, we say that the confinement is 2D parabolic confinement. And for this case, the closed cell configuration is 2E, 6E, 12E, 20E, and so on. So the first cell will occupy 2 electron, second cell will occupy 4 electron, third cell will occupy 6 electron, and fourth cell will occupy 8 electron. So when if you see this current through this quantum dot region, we see that when you add one electron one by one to this system, there will be a peak because of this two electron. Then there will be a gap because of this energy spacing. Then there will be a peak because of 4 electron. Then there will be a gap. So the gap will repeat. So this is, I think, this is all about what we have seen, more and less what we have seen in week 7. We have also seen the effect of magnetic field, and we have seen that if we apply the magnetic field, the spin state will split. So instead of a single peak, we will have a splitted peak, each corresponding to a spin state. Okay. And what else? I think this is all. Now let us solve the problems related to uh, week 7, and also we have not covered some of the problem of week 6. So let us try to solve it first, then we'll move up to week 7. So the first question is, in the large bias limit, why does I is I L minus 1, sorry, minus L, or the right propagating wave, and how does this differ conceptually from small bias Ohm's law? A, right moving states from right are suppressed and it becomes non-ohmic as I is no longer linear in V. Option B, all states contribute equally and it remains ohmic. Option C, transmission drops to 0 and the current saturates. Option D, spin degeneracy is lifted and conductance is half. So how this large bias limit is different from this small bias limit which satisfy the Ohm's law? Is it not visible? Okay. Okay, option A. Yes, it is correct. So for large bias limit, the right propagating wave, it is suppressed and it is a non-ohmic behavior. Okay, let us move to next question. In the very low temperature limit, the use of, we have a low temperature limit. And it is asking what does dou F by dou E, which is equal to delta E minus mu signify. So what does this conceptually means in a low temperature limit? So option A is, let me omit. Okay. Option A, all transport occurs through bulk state away from the Fermi surface. Option B, broadening dominates, making conductance energy abreast. Option C, transport is sharply confined to the Fermi surface and the conductance probing T mu only. Option D, current becomes independent of the bias voltage. Option C. Yes, it is correct. So transport, it would be, because in the low temperature limit, there won't be any broadening. Broadening is, it can be minimized. So because of that, we mostly focus the transport around the Fermi surface. Okay, question number 10. For a gallium arsenide two-dimensional electron gas, so we have gallium arsenide two-dimensional electron gas with shade density Ns is 3 into 10 to the power 11 per centimeter square. Calculate the Fermi wavelength lambda f and then estimate the number of transmitting modes in a quantum point contact with constriction with 120 nanometer. So first we need to calculate what is the Fermi wavelength. Given that the seed density is 3 into 10 to 11 and also it is given it is a two-dimensional electron gas. Okay, so let me go through the steps. So if you see the question, the clue is already given. It is a two-dimensional electron gas, right? And for Fermi wavelength, what we need? We need the wave vector because the Fermi wavelength it is related to the wave vector by this formula 2 pi by k. So all we need is what is k for this system, and it is already given. It is a two-dimensional electron gas. So that means we can use the expression of K for the two-dimensional system. If it was given 3D, then you could have used 3D one or 1D. For 1D, you should use 1D case. But it is given it is a two-dimensional electron gas. So you should use the K expression for the two-dimensional system. And this we have already, if you recall our previous lab session, we have already derived what is the value of K. So I'm just writing down the final expression. So K for the 2D, it is given by 2 pi Ns to power half. Ns is the charge density, or here it is the sheet density. It is given 3 into 10 to the 11. So let us calculate it. So square root 2 pi 3 to 10 to the 11 per centimeter square. So it will give 10 per 15 per meter square. And this will be 1.37 to 10 to the 8 meter inverse. So we know kf, lambda f now will be 2 pi 1.37 10 to the 8. And if you calculate it, it will come around 45.8 nanometer. So answer for this is 1 minute. Estimate the number of transmitting modes in the construction. Okay, so whatever values are given, it is what is the number of transmitting mode that he will find. So this won't be nanometers. So these are unitless because these are number of modes. So we have calculated what is cave. I hope the answer is correct. 3.6. Okay. So N, now we can calculate. If you recall the number of transmitting mode, it is given by 2W by lambda F. And W is the width of this construction, which is given 120 nanometer. So 120 nanometer divided by 48.8 nanometer. So this will give a value around 5.24. Let me cross check whether the answer is correct. The steps are same. You just need to use the two-dimensional electron gas to calculate kf. Then from that you can calculate lambda f. And if you know lambda f, then calculating the number of modes, it is quite easy. Yes, the numbers are correct. So that means the number of modes is A, option A. So is it clear? Should I move to the next problem? The next question, we have, this is a conceptual one. We have a gallium arsenide quantum point contact, which has two-fold spin degeneracy and no valley degeneracy. It supports three occupied 1D modes at the Fermi energy under certain gate voltage condition. Assuming ideal transmission, what is its conductance? Option A. So there are three occupied 1D 1D modes, and it's also given, it has a spin degeneracy of, or it has a two-fold spin degeneracy. So if there is a degeneracy, then we have to take that into account. So each degeneracy will also give a conductance value. So what will be the answer? So answer will be option B. So if we don't have any degeneracy, then the conductance is 3 e square by h. E square by each mode will have e square by h, and 3 occupied level will have 3 square by h. But now it's given it is a two-fold spin degeneracy. So for each mode, there are two spin state, and for each spin state we have a conductance of e square by h. So that means each mode, because of this two-fold spin degeneracy, will have a conductance of 2 e square by h, and there are three modes. So we'll have a conductance of 6 e square by h. Okay. And also if it was given there is a valid degeneracy, then also you need to take into account the valid degeneracy factor. So if you recall, for the bilayer graphene, we have a valid degeneracy also. In addition to spin degeneracy, we have a valid degeneracy. So for that case, if we recall, the conductance of each level is 4 times e square by h. Okay. Okay, question number 12. In the quantum ballistic regime for a 1D channel, where does the power dissipation occur, and why is the conductance finite despite no scattering in the channel? So the question asks, if you have a quantum ballistic region, then ideally there won't be any scattering. Okay, but in reality we see that the conductance is finite and we see a power dissipation. So what is the reason behind this power dissipation and the finite nature of this conductance? Option A, thermal broadening. Option B, at the channel, due to the electron interaction, we see a power dissipation. Option A, it is due to the interaction between the 2D continuum region of 2D electron gas and 1D discrete channel. Or option D, resistance experienced at the source and drain side. Yes, your correct answer is option C. So whenever the 1D discrete channel of this quantum dot region, it meets this bulk, it has a different energy level. Whenever they meet, we'll see a resistance. I think this is the last question. Then we'll start from week 7. Okay. Contact resistance depends on number of modes in the channel region of quantum point contact, or it depends on the applied voltage between source and drain, or option C, electrochemical potential energy of source and drain, or it depends on all of this above. What is the dependence of contact resistance? No. Answer is option A. So if you recall, the contact resistance is given by H by 2 square 1 by N. So that means RC depends on the number of modes in the channel region. Okay. This okay, we have 2 more questions. Then we'll start from week 7 question. Okay, question number 14. A gallium arsenide quantum point contact at zero magnetic field shows a conductance plateau due to two-fold spin degeneracy. What is the spacing between successive plateaus in this case? Okay, you mean E square by H, but if you see that it's given a two-fold degeneracy. So that means the conductance of each level, it is given by 2 square N by H. N is the number of modes. So that means the spacing will now, if you take Gn plus 1 and Gn instead, the spacing will be 2 square by H. Whenever you have a two-fold degeneracy. Option B. Question number 15. In a bilayer graphene, quantum point contact is zero magnetic field. Conductance plateaus are observed at 4, 8, 12 in units of A square by H. What is the physical origin of factor of 4 in this plateau spacing? So why there is a 4? Whether the 4 is because of 2 spin state and 2 valleys, or it is depends on the layer degree of freedom. That is, it is a bilayer graphene, that is why we are saying 4. Or option C, both A and B are correct. Option D, none of them. Which one is the case? Yes, option A is correct. So for bilayer graphene, we have two valley degeneracy as well as two spin state degeneracy. Because of that, we see that the conductance of each energy level is 4 times E square by H. Okay, so let us move to our questions related to week 7. First question, say conceptual one. So it says, what is sorry, why must the tunnel junction resistance in a single electron transistor typically satisfy R greater than H by E square? Option A, to increase the heating of device by Joule dissipation. Option B, to ensure that electron tunnel coherently as a wave. Option C, to guarantee that the Coulomb blockade effect disappear. Option D, to keep quantum fluctuation of charge small so that charge on the island is well defined. Which one of this option is correct? You think it is option B? No, the actual okay. So the Answer to this question is option D. So why option B is not correct is that it says to ensure that electron tunnel coherently as a wave. So if electron tunnel coherently, that means we won't see any Coulomb blockade effect. So this is the Coulomb blockade effect condition, right? So we need that the tunnel junction resistance would be greater than H by S square. This is what we mean by Coulomb blockade effect. But if the electron tunnel coherently, that means uh, we won't see any we won't see that we are adding electron one by one. We will see that the current electron is flowing continuously through this tunnel junction, and it will satisfy the normal conductor IV characteristics. So we won't see any oscillation in the current because of the Coulomb blockade effect. So the main reason why there is a tunnel resistance is that to see this Coulomb blockade effect or to see this single charge effect. So by Coulomb blockade effect or by single charge effect, what we mean that we are for this system we are adding charge carrier one by one. So electrons are not flowing continuously; it is getting added or it is getting removed one by one. So we'll see a step-like manner in the change in the charge density of this quantum dot as a function of the gate voltage, or we'll see there is a oscillation in the current because of this tunneling. Okay, so for this to happen, so for charge carrier to be well defined in this region, in this region, in this region, and in this region. So for that, we need that the island, this island must be they by island means I mean the quantum dot region or the classical dot region. Okay, so this island must maintain the integer states of this uh, charge carrier without any strong quantum fluctuation. So the fluctuation in the charge carrier shouldn't be there. It should be well defined. So that only in that case we will say that we are adding charge one by one. So so to achieve this, to achieve that the charge carriers were well defined, we need that the junction resistance or schematically what we if I want to draw. So this quantum dot region, it is tunnel coupled to the source and the drain. So there is a tunneling region between source and drain which prevent the continuous flow of charge. So this tunneling region, so this is the tunnel junction between the dot and the source and the drain and the dot. So this RT, it should be greater than H by A square. So what will happen for this high voltage that for this high voltage, we'll see that the tunneling of electron from the source to drain, it won't happen quite easily. So it will happen only when it satisfies some condition, which we say the Coulomb blockade condition. Okay. So whenever this RT is greater than H by square, then this island, it is effectively isolated from the source and the drain. Okay. So that means the charge carrier that is present in this island, it remains as an integer. So the charge carrier is well defined in this region. Okay. And so only when the EC, only when the VG, when we apply a gate voltage which satisfy this, which lowers down the n+1 energy level, only in that case we'll see a tunneling from source to dot and dot to drain. So that is why we need a tunnel resistance so that the electron can't flow easily from source to drain and from from source to dot and from dot to drain. So I hope I'm clear. If not, let me know. I will try to clarify it further. So answer to this question is option D. So AT is there to maintain, to keep the quantum fluctuation of charge small so that the charge on the island is well defined. So is it clear? Uh, what happen when we apply gate voltage? Okay. So when we apply gate voltage, what will happen? So if you recall the electrostatic energy, it is given by Cg Pg minus Na square by 2C sigma. So this gate voltage, what it will do that this quantum dot, they have a energy level, right? So it is a, let's say it is energy level like this. So here we have a n state, here we have a n plus 1 state, n plus 2 state, n plus 3 state. So for zero gate voltage, we say that initially the island, the quantum dot, it has a n number of electron. Initially it is n. So for that case, it is the energy level is properly aligned with the source and the drain. There is a source part, there is a drain part. Now, when we increase the gate voltage, what it will do? It will lower the energy of this quantum dot. So it will lower the energy of E1 plus state so that it will come here. Okay. And it only happen at a certain gate voltage. So if you see the graph, only in this region we will see that there is a increase in the conductance. So it is not like you just put a random gate voltage and you will see the Coulomb Blockworth effect. So it's not that the case. So only when the n plus 1 state is properly aligned with this energy level, only in that case we'll see a quantum conductance. And this happens when the energy level of En it matches with the energy level of n plus 1. So we are pushing the n plus 1 state to the n state so that they have the same energy. So for this case, what will happen? The electron will have, and it can have energy E, it can also have uh, energy E n plus 1. So that means if you now add this electron, it's not sufficient to tunnel from source to dot and from dot to drain, because now the En is equal to En plus 1. So it's possible to possible for the electron to occupy this n plus 1 state, because this n plus 1 state is the energy is lowered by means of this gate voltage. Okay. This is in brief what the gate voltage do to this energy level. Okay. Question number 2. The charging energy is C of a classical dot. It is mostly directly determined by total capacitance seen by the dot to all electrodes and gate. Option B, dot single particle level spacing. Option C, Fermi energy of source electrode. And option D, transmission coefficient of tunnel barrier. So charging energy EC, how you can determine the charging energy? What is the which factor you should know to calculate the charging energy? Whether it is the Fermi energy of electrode that gives the charging energy, or the single particle spacing in the dot, which keeps the charging energy, or the transmission coefficient, which keeps the charging energy, or the C total. Which one of this is correct to calculate the charging energy? Okay, so the formula for calculating the charging energy EC is given by, so you should remember this, E square by 2C sigma. So E is the elementary charge, which you take 1.6 into 10 to the minus 19, and C sigma, it's the total capacitance of this circuit. So you have a capacitance because of this gate, we have a capacitance because of this source, and also because of this drain. So this will also take in account the capacitance because of all the elements that is present in the nanoscale device. So that means AC you can calculate it if you know the total capacitance seen by the dot to all electrodes. Option A. Okay. Question number 3. In a Coulomb blockade experiment, sweeping the gate voltage Vg at low bias reveals periodic conductance peaks as a function of Vg. So you are wearing the Vg at low bias, and we are seeing that there is a periodic conductance peak as a function of the gate voltage. What does the spacing between the adjacent peak primarily correspond to? So what it says that, so you are varying the gate voltage and you are seeing the conductance, or let's say current, and you are saying that there is a periodic peaks that you are seeing. The question is asking, what does the spacing between this adjacent peak primarily correspond to? Option A, difference in Fermi level of source and drain. Option B, energy difference between the ground state and the first excited state within the dot. Option C, the change in electrostatic energy required to add one electron. It is converted to gate voltage via gate capacitance. Option D, none of the above. What does this reason correspond to? Option D, none of the above. Okay, so let us see first. Then, actual answer to this question is option C. Okay, so if we recall this conductance peak, when we'll see this conductance peak, we'll see this conductance peak whenever the energy of n state matches with the energy of n plus 1 state. That means the electronic state aligned with the charge degeneracy point. And the spacing between this peak, this correspond to the energy which is required to add or to remove one electron from n state to energy required to add one electron or remove one electron from this quantum dot region. Okay, so this spacing, which is Cg delta Vg. So this is equal to E. Okay, so this says that whatever the energy, the spacing is there between this periodic oscillation. So this corresponds to the electrostatic energy which is required to add one electron, and this is converted to the gate voltage via gate capacitance, which is the CG delta Vg is E. Okay. So in brief, the spacing, it corresponds to what is the energy required to add one electron to this system, and this energy, it is given as Cg delta Vg, which is equal to E. Okay, so is this clear? Okay. Question number 4. This is also a conceptual one. What is the physical role of tunnel barrier in quantum dot showing Coulomb blockade? So why do we have a tunnel barrier between source and the dot, and from dot to drain? Option A, they increase the dot's capacitance, thereby reducing the charging energy. Option B, they ensure the dot's energy level become perfectly continuous rather than discrete. Option C, they isolate the dot electrically from the leads, making electron transport probabilistic and discrete. Option D, they provide strong magnetic field that split spin state via Zeeman effect. So why do we have a tunnel barrier? So we say that the dot is tunnel coupled to this source. So by tunnel coupled means with that there is a resistance there in this tunneling region, and also there is a resistance there, the drain. So why don't we attach drain directly to the dot region and also directly to the sources? Why do we have a tunnel junction here? So this is somewhat related to question number 1. So why do we have RT in the first case? So the main reason that we have RT is that, let us say we don't have any RT. So what will happen? The current will flow continuously from source to drain. Okay. Now we have a RT which is much greater than H by A square. So what it will do that? So because of this finite tunnel resistance, which is much greater than H by E square, so this barrier, this tunnel junction that we have on source and the drain side, they will prevent any direct conduction of charge carrier from source to drain. So that means if they prevent it, that means the number of the charges that is present on this quantum dot region, it remains quantized because there is no continuous flow of charge, because there is a tunnel barrier present here. And the charge carrier can be added to this tunnel junction only when uh, the charging energy is it is much lesser than the gate voltage. Okay, so that means the tunneling will happen only when we have a sufficient gate voltage or sufficient source to drain voltage, which will overcome the charging energy. So this says that the tunneling is probabilistic. Okay, so that is why the answer to this question is option C. So The tunnel barrier is there to isolate the dot electrically from the leads so that it will prevent the continuous flow of charge carrier, and it will make the charge in the quantum dot region is quantized, and also making the electron transport probabilistic and discrete. Okay, so I hope the explanation is correct. If not, let me know. I will try to clarify it further. So, of question number 5, it's a numerical problem. So, it's given for a tunnel junction with the capacitance 0.5 attofaraday RT. It is given 100 kilo. What is the RC time constant? So, can you please calculate it? Option B. So RC time constant is, it is nothing but RT time C. C is given 0.5 into 10 to the minus 18 and RT is 100 kilo. So this will give 5 into 10 to the minus 40. Option. So what does this RT time constant physically signify? This RT time constant, this is it's in the time scale. So this indicates the characteristics time between two successive tunneling event. Okay. So this is the physical significance. So it says the time between tunneling event. Okay, question number 6 for the above tunnel junction, which have RT is 100 kilo and C is given 0.5 attofaraday to minus 18 Faraday. So for this tunnel junction, what is the maximum temperature at which you would expect the Coulomb blockade effect? What is the temperature at which, what is the maximum temperature where you will see the Coulomb blockade effect? So keep in mind that whenever you are trying to solve any problem, just check whether RT is greater than H by E square or not. If it is not greater than E square, then there is not Coulomb blockade effect and there is no point of solving the problem. But here you can clearly see it is greater than 25.8 kilo. So that means it's possible to see the Coulomb blockade effect. So always cross check this condition before solving the problem. So what is Tmax? It's quite straightforward. You just need to check the first condition that is required for Coulomb blockade effect. So 25.5. So if you recall the Coulomb blockade effect, one of the condition we have is that the tunnel resistance, which is RT, should be greater than H by E square. And if you put the value of H and E square, H is 6.63 into 10 to the minus 34, and E is 1.6 into 10 to the minus 19 square. So if you calculate it, it will come around 25.8 kilo. So that is why I said always check whether the tunnel resistance is greater than 25.8 kilo ohm or not. So if it is greater than 25.8 kilo ohm, then there is a sufficient tunnel resistance which is there in the circuit, and it's possible to see the Coulomb blockade effect. So is this clear? The 25.8 part? Okay, to solve it, you can recall the one of the condition of the Coulomb blockade effect. So in total, there are two conditions to see the Coulomb blockade effect. So if you want to see the Coulomb blockade effect, so one condition is that the charging energy EC, it should be much greater than the thermal energy. So by this condition, we mean that the thermal energy is much less, so that whatever the charging, the transport is happening because of this charging energy. So if the temperature is not that low, what will happen? We'll see a broadening of this Coulomb oscillation because of this finite temperature. Okay, so this because of this broadening, what we'll see, the quantized, we say that the charge is quantized and the charge is added one by one. But if the temperature is not low, then it's not possible to see this tunneling of electron one by one through this dot reason. Okay, so the first condition is the charging energy should be much greater than kBT. And the second condition that we have seen is the tunnel resistance RT should be greater than H by E square, which is 25.8 kilo. So we need to find out the maximum temperature. So we can make use of this first condition, that is EC, which is E square by 2C. It is the charging energy. It should be greater than kBT. That means temperature is less than E square by 2C kB. You can just put the values. C is given 0.5 and kB is the Boltzmann constant. It is around 1.38 into 10 to the minus 23. So if we solve it, it will come around 18.55 Kelvin. So the T should be less than this value. So maximum value of T should be 1855. Option E. Okay. Question number 7. It's I think you will be able to find out the answer. It says, what is the minimum tunnel resistance for observing the single electron effect? What is the minimum resistance required? Yes, option A, which is H by E square. Question number 8 says, in a SET means single electron transistor, the Blockwood threshold voltage is okay. So it's given a single electron transistor and the effective capacitance is also given 0.5 to 10 to the minus 18 Farad. What is the threshold voltage for Coulomb blockade? So threshold voltage is that what is the minimum voltage that is required to see the tunnel. So, and if you recall the graph, so the minimum voltage is required is E by 2C. Sigma. E is 1.6 10 to the minus 19. 2 is okay 2 and zero point 0.5 into 10 to the minus 8. I think it will come around 0.16. This is 1. Yes, 0.16. Option A. Okay, so let us solve the last problem. It's given in a stability diagram, which is the plot of differential conductance versus the source drain bias VST and the gate voltage VG. Coulomb blockade region often forms diamond-shaped area of suppressed conductance. What does the size of Coulomb diamond in bias direction primarily represent? Whether it is represent the maximum possible current that can flow through the device at that gate voltage, or option B, the difference between source and drain capacitance to the dot, or the energy gap between the highest and lowest occupied level, or it represents the range of bias over which no energetically allowed single electron tunneling transition exit between n and n plus or minus ones. State. Okay, if you have doubt, you can ask now because we have only 5 minutes left. So it's better if I clarify your doubts first. So what doubts we have? Can you please specify? Mm, mm. Yes, you are unmuted. You can speak now.
Hello, ma'am. Good evening. Ma'am, actually, I have
Hi.
doubt on score, ma'am. They did not provide 0 0.5 score for multi-select options. They are saying that even if you select one incorrect answer, will not provide the score. But whereas for other NPTEL exams, they are providing 0 0.5 and partial marks also. So that's the main reason I am not getting the score here.
Okay, so you mean that for that question, one of the option is correct and you forgot to, and
Other
other
option
option
is,
is not.
yeah.
Okay. I think you
So
have already raised the
yeah, I
same
have
during
raised,
the.
ma'am. Some Hari sir is there. He's saying that even if you incorrect one answer, will not provide the score. So I said that please to provide like at least for point 0.5, like we will increase the score, right? I think you understand my problem.
Yes, 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 I do understand, but
See, yeah, I'm not
I
like that
can't do
much physics
anything.
student, so even I'm trying hard. I'm seeing the live sections, seeing the all the lecture videos, number of times to solve the
Yes, yes,
assignment. So I
yes,
just I'm
yes.
sharing my problem. That's it, ma'am.
Uh, See, it's like the marks is up to them, so it's not in my hand. So whatever they decide, it's the final one. So I don't
Okay.
think even if I say something, it won't matter that much because it is all decided by the course instructor as well as the TAs. So I don't
Okay,
think
ma'am.
it will happen. So I would suggest that please be careful next time so that just look at the option which you think. Don't uh, uh, just correct. Sorry, just if you are finding out that one of the option is correct, so always check whether the other options are correct or not. Okay, always cross check, and if you're finding that two of these options are correct, then you should mark both this option. Okay, so please be careful next time because I think what is already done, we can't do anything about that. But you can
Yeah, ma'am. Okay.
also rectify your mistake in the next assignment. Okay.
Yeah,
Do you have
ma'am.
any
Just
other doubt?
one more doubt, ma'am. Like you are from IIT Delhi, right? And this course is from
Yes.
ISAR Trivandrum. So how can you be the TA for this? Like, uh, you are from Delhi and this course is from
Okay.
Thiruvananthapuram.
So it's like so actually I am a PMRFTA. So for us, we have to do some extra TAs outside our institute. So for that, it's like there are many methods to do the TAs. Like you can take the NPTEL TA course, or you can also do some TA in nearby schools. So what I'm doing is that I'm
Okay.
just uh, whichever course is, I think I can do the TA for that course. I just request the course instructor, and if they allow me, then I can do the TA. So
Okay, ma'am.
NPTEL is different. They are the one they are the one which decide the questions and answers. So I'm just here to clarify your doubts and give you more questions so that you can understand the concept better. Also, you can get extra set of question that can help you in the final exam also.
Yeah, ma'am. This live session questions are somewhat easy, ma'am, compared to assignment.
It's like you can ask your doubt directly to me, and I can
Yeah.
try to clarify your doubt. If not,
Yes,
then I
ma'am.
can
You'll
also
explain in
do.
easy way, ma'am. I like this section. So even if it is late, if
Okay,
it,
okay.
I will
Thank you.
I will attend this session. Okay, ma'am. Thank you
Okay,
so
thank you
much.
so much. Okay. Okay, thank you for the joining this session. So we'll meet on next Friday, same time from 6 to 8 to solve few more questions, as also to go through the concept of week 8 in detail. Okay, so we'll stop for today. Thank you for joining the section. Goodbye, everyone.